let's go. Break it down, put it there, bring it on, step it up, right there. Break it down, put it there, here we go. Step it up, bring it on, let's go.
Welcome to your screen, welcome to Streaming Generale, but most of all, welcome to this lecture. This week, in between all my video calls, now and then a YouTube video, on my mails, apps, tax return, looking online for information and so on, a thought crossed my mind. How would this pandemic lockdown be without phones or laptops? Would I, for example, be able to do my job as effective as now? Would it for you students be possible to take exams or have any means of proper education? The most simple answer, according to me, is nah, definitely wouldn't be the same. Although a lot of us do feel the need to get off the screen, I think we do appreciate the technological revolutions in computers and phones. It made our life a lot easier, and that's an understatement. The main components you find inside your iPads and smartphones are semiconductors fabricated from silicon, which is one of the most common constituents of sand. In this lecture, University of Maastricht lecturer of physics and academic jack of all trades, Dr. Donna Carroll will explain, amongst other things, how we went from a simple particle of sand to a complicated modern electronic device. Donna, the screen is yours.
Fantastic. Thank you very much for the introduction. It's very nice to be here. I'm going to start by asking you, actually, so like outside of like food, drink, shelter, what is the one thing that you can't live without in your life, right? And I think if I were to ask most people that question, they would say, as David said, yeah, like our phones, our technology, our lives are so dependent on these things. And yet it's really rare that we ever stop to think, well, actually, what's going on inside our devices? How are they made and how do they work? We very rarely stop to think about that. So that's what I want to talk about today. And I kind of want to start by talking about a material, and it's the material that all of these things have in common. So your mobile phone, I've got a glass here that I'm drinking out of, so it's a material that's in that. Let's see what else. The bricks in the building that I'm in, right? And yeah, also, you know, it's handy to have a cooking spatula with you. Well, all of these things that I've pointed out and shown, they all have one thing in common, and that is, as David said, is silicon. And silicon is an element in the periodic table. It's actually, for those chemists among you, it's element 14 in the periodic table. And it's actually is the second most abundant element in the Earth's crust. And the reason why is because, as David said, it's one of the main constituents of sand. So if you look at what's sand made out of, it's made out of silicon dioxide. So for every silicon atom, you have 2 oxygens. So of course, if silicon's the second most abundant element on the Earth's crust, and we know that oxygen is the first. But yeah, silicon, it has all of these really useful applications, right? So I've already said, if you look at the building materials, right, we use sand for that. So we use it for building materials, concrete, brickwork. We use it to create ceramic items. Also, if we heat sand and we make it into its liquid form, this silicon dioxide, we have 2 choices. We can let it cool back into a solid really fast, and then we get glass. Or we can let it cool really slowly so that some sort of regular pattern forms. And then we get quartz crystals. And without these 2 things, glass and quartz, science wouldn't have evolved in the way that it has today, right? Because we use quartz for timing devices, for our watches, for instance. And we need glass for microscopes and for telescopes. So without these things, you know, science wouldn't have advanced in the way that it has. You can do a lot more, you know, I got my spatula out. If you mix silicon dioxide with hydrocarbons, you can also make silicone. You've probably all heard of silicone. And you can make all sorts of different, like, kind of rubbery, high temperature, stable things out of these, including breast implants, cooking materials, piping, and it's also used in shampoos and stuff. But what I want to talk about for the next half an hour or so is this material here, right? It looks like a metal, it's shiny, it's beautiful, it's not a metal. What this is pure elemental silicon, right? So if I'm talking about pure elemental silicon, sorry, I have a thing that's appeared on my screen. Aha, there it is. Okay, so if you're talking about pure elemental silicon, this doesn't exist in nature, right? So this is something that we actually have to create. And how do we get this? Well, what you do is you start with a furnace. You take your sand and you plunk it in the furnace, so you're heating it up, right? And then you add charcoal or coal. And for the chemists among us, you basically have a redox reaction. And what that means is what you get coming off is carbon monoxide as a gas, but you get pure silicon that drains out as a high temperature liquid. And that's where you get your pure silicon from. Now, I don't know whether any of you guys have ever made a candle, but if you're a child, sometimes you get to do these things, right? What you do when you make a candle is you have a piece of string usually, right? And you dip it into your liquid wax and you dip it in and out, and the candle sort of grows wider and wider in the end, and you end up with a candle like that, like a cylindrical candle. And it's an oversimplification, but that's basically what they do with their molten pure silicon, is they create a giant candle out of it. And when I say a giant candle, it's nothing like this. In fact, here are some photos of what this looks like. So you can see this is a candle of a completely different scale, right? You can see here it's almost the size of a person. And basically, you've ended up with a sort of silicon sausage, let's say. And what do you do with sausage? Well, you want to slice it up. So that's the next step in the process. And you end up with what we call, these are silicon slices, but we call them silicon wafers. And it's these wafers that all of our microchips are made out of. And in fact, the reason why we call them chips is because they are a chip of silicon, of these silicon wafers. And these silicon wafers are incredibly pure. They're 99.9% pure silicon. And in fact, if you pull apart any modern device, so here's one I pulled apart earlier, and you take a look inside. So this is an old mobile phone, and you see inside, you see all these black things, right? So little black squares everywhere. And it's these little black squares that are our chips. And these are made out of this silicon material, these silicon chips. And I guess the question is like, well, why silicon, right? What's so special about silicon? Well, you've probably heard of conductors and insulators, right? So we know that conductors conduct electricity and insulators don't. But yeah, silicon is neither of those things, right? So in order to explain how silicon behaves, let's quickly look at how conductors conduct. So I'm very quickly gonna swap my presentation and show you a quick animation. So let's show you this here. Hopefully you can all see this now. So in a material that conducts, like a metal, you've got here, you can see your positive nuclei of all of the atoms in the material. And in a conductor, you have free electrons. So these are electrons, they're the little blue ones that are bouncing around. They are free to travel through the material because they're not involved in the bonding process, right? Now, if I then attach a battery or an electric field across this thing, well, we know that electrons are negative. So if we make one side, so if I'm going to make this side, the right side, I'm going to make it positive, then those free electrons will be repelled from the negative side towards the positive side. And that is the conduction of electricity that I'm talking about, right? Electricity is the flow of electrons. So that's what's happening inside a conductor. So how is silicon different? Well, let me switch back to my presentation. Excuse me just a second while I find all of the right buttons to click. Okay, so silicon is different, right? Because it's not a conductor. And if I show you the periodic table here, you can see that actually silicon is in group 4 of the periodic table. What that means is that it has 4 electrons in the outer shell. And it's those 4 electrons in the outer shell that determine its properties, essentially. So when it's in a material, excuse me just a second. So when it's in a material, the way that it bonds is that it shares all of those 4 electrons with the other silicon atoms. And unlike the conductor I just showed you, it doesn't have any free electrons, right? So if I attach a positive terminal and a negative terminal, you see that there aren't any free electrons, so no electricity can flow, no current can flow. However, this is where silicon is interesting, because if I add energy to the system, and that energy can be in the form of heat, or it can be in the form of light, well, that is enough energy for some of those electrons that are involved in bonding to break free. So you can see those little, I've colored them red here, but those little electrons, they get enough energy and they break free from their bonds. And that means that we've created these free electrons in our material by adding energy to the system. And now if we apply a positive and negative terminal by using a battery or a power supply, those electrons will be able to flow across the material. So it's like if you had a circuit diagram, if you're aware of circuit diagrams, we could have a semiconductor and a circuit, and at low temperatures, nothing would happen, no conduction. But if we were essentially to add energy to the semiconductor by heat or light, we would get then current to flow in the circuit. So that's how it's very different from a conductor and an insulator. An insulator doesn't ever have free electrons, and a conductor always has them. And these semiconductors, we call them semi, they're halfway, right? They're halfway between the two. Something else interesting about silicon is not only does it have these electrons that can carry current across the material, but I don't know whether you can notice from this diagram here, but where the electrons have sort of popped out from their bonds, they've left behind what we call empty holes. And those holes can also conduct electricity. And you're kind of thinking, how can a hole conduct electricity? Well, it's more the absence of an electron. So you can look at it as sort of like a traffic jam. So here we have electrons in a material with a hole, and there's a hole because that electron has gained more energy and it's left that bond. And all of the electrons will move into that hole once you apply a voltage across the material. And that means that even though it's the electrons moving towards the positive supply, it kind of looks like there's a hole going in the other direction. So that's the other thing that makes semiconductors different from conductors. It's not just electrons that are doing conducting. We also talk about these holes that move across the system and conduct electricity as well. So they're not by themselves as good as a normal metallic conductor. When we talk about how conductive a metal is, because we've got electrons free to flow across the system all of the time, if we increase the temperature of the material, all of the atoms start vibrating because they get more energy, and they actually block or impede the flow of electrons. So we call that resistance, right, to the flow of current. So the resistance for a metal or for a conductor, it increases as temperature gets higher. So if you look how well a conductor conducts, it gets worse and worse as you increase temperature. But because a semiconductor relies on having extra energy from an increase in temperature to get the free electrons, it has the opposite effect. As we increase the temperature, you get more and more electrons, so you get more and more conductivity. But you can see from this graph that the conductivity of a semiconductor isn't quite as good as a conductor. So you have to do this thing called doping. And we normally talk about doping when we take impurities ourselves and it enhances performance. It's exactly the same thing. So in this material, I'm talking about silicon, it's in group 4 of the periodic table. If I take something from group 5 of the periodic table, it has an extra electron that isn't involved in bonding, so that can increase the conductivity of my semiconductor. And if I take something from group 3 of the periodic table and I put it into my silicon, well, that's got an extra hole because it's got one fewer electron. So these things can also help with the conductivity. So here you see this is pure silicon. I can swap a silicon atom out for phosphorus, which is group 5. I end up with an extra electron, and that can increase the conductivity and make it better. Or the other way around, I take something from group 3, which has one too few electrons to share with the rest, and you end up with a hole that can do the conducting. And by doing this, we can change the properties of all these semiconductors. And that's essential because we want to change the energy that is required to create conductivity in a semiconductor. And that means that we can create all sorts of different semiconductor materials with different properties. And actually, you know, I'm basing my talk around silicon, but it's not the only semiconductor. You can make semiconductors from other elements in the group 4 of the periodic table that you see here. Although silicon is the most commonly used and we know more about silicon devices than anything else. But you can also do this mixture between group 3 and group 5 atoms as well. And the applications are really broad, right? Because you're talking about absorption of energy to make an electrical signal. So when do you need to do that? Well, if you're building any sensor device, right, you want to sense changes in heat, or you want to sense changes in light, then you can use a semiconductor. So we use it for all sorts of sensors, security sensors, solar panels, because we're converting from light energy into electrical energy. We can detect radiation using these, infrared radiation, and we use them in our digital cameras. So these devices are everywhere around us. Not only that, but because it's about absorption of light, it actually changes how some of these materials look. So diamonds, you get different colored diamonds. Now, diamonds are also a semiconductor, because if I show you the periodic table, carbon is also in group 4. So it's a semiconductor device as well. And this is interesting because if you find natural diamonds, the color will tell you about those impurities within the semiconductor structure, because you're absorbing, those impurities are absorbing energy at a certain wavelength, and what we see is the energy that hasn't been absorbed. So that gives it its color. And if we create man-made diamonds, we can change the color that they look like by changing those impurity atoms. So it's very interesting in its applications, and not only for coloring diamonds, but for coloring LEDs. So LEDs are all made out of semiconductors, and they've helped to revolutionize light, right? Because the way, light used to be very inefficient and expensive, and now LEDs are very efficient. They don't use much energy, and it works in the other way around. So we talked about, you get your pure silicon and you give it energy, and these electrons gain the energy to conduct. Well, your LEDs are conducting electricity, and when those electrons relax, they give off energy at a certain wavelength, and that's what gives the LEDs their color. So these are amazing revolutions in our technology already. But the biggest revolution that semiconductors and silicon has had on our daily lives, to explain that, I need to go back to a bit of history, and I'm going to carry on talking about light bulbs, right? These pictures are of the first light bulbs that were the first filament lamps that were ever made. And you can see here, they had real issues when they tried to create light bulbs, right? Because the filament would get very hot. And you can see on these pictures, the surface of the glass would go really dark. And the reason why was the filament was getting so hot that tungsten was being given off, and it would deposit on the light. And that was really inconvenient for lighting, right? Because your lights are going dark. But actually, not only tungsten was being given off from the filament, but electrons were getting so hot and so energetic that they were also being liberated from that hot filament. And yeah, very inconvenient for creating lighting, but actually very useful in a different sort of device. And that device is here. You can see this picture. So that device we could really manipulate to help our technology, right? So here you can see it kind of looks like a light bulb, and you can see you've got the filament of the light bulb. So you've got a small power supply that is supplying that small filament. And now if we take advantage of this fact that electrons are being given off from the filament, well, if we put a plate, so you can see a plate here at the top of the bulb, and if we charge that up and we make it positively charged, then you see that the electrons will be drawn to it and it will complete the circuit. Now, that's interesting for two reasons, right? Because it means that we have a power supply here on the right-hand side, and it means that we can use that power supply to switch this bulb on and off, right? Because the electrons will not be able to go to the metal plate unless the power supply is on. So we can use this device as a switch. But more importantly, you can use this device as an amplifier, because if I add another little wire in between the filament and the metal plate, and I put a very small signal, small electronic signal through there, well, because I have a small electronic signal, and that will modulate the way that the electrons are crossing that device, what you get measured out is a replication of that small signal, but much bigger because the power supply on the other side is much bigger. And this is amplification, right? Because I have a very small signal and I replicate it and I essentially enlarge that signal. So these devices could be used as amplifiers, right? And these had a huge impact on the world around us because this is a map from 1891. And this is when they first started putting the telephone lines in America. And you can see in 1891, they didn't get very far across the country. These are the only telephone lines that AT&T had installed. And the reason why was the signals were so small, they couldn't extend the network across the whole country until these bulbs that we now call valves or tubes, we needed to invent those and use them as amplifiers in order to get the telephone system network across the whole country. And here, this is about 30 years later, and all of these black lines, they're the telephone grid system that was put in place once we had this technology. So I said they're not only useful for amplification, but you can use them as switches. You can turn them on and off. And for anyone who knows anything about computing, on and off is really important because they give us two states, a 0 or a 1. So 0 when it's off and a 1 when it's on. We call that binary information. The information is of two sorts. It's either a 0 or a 1. And this is how all computation is done. So computers communicate and store information and compute all in this binary system using zeros and ones. So not only could these valves be used for amplification, they could be used for computation. And so you see here they're used as amplifiers and switches. And this, you know, it's a big challenge because these valves are huge, right? This is a little one that I'm showing you now. So this valve here is quite a small valve. But really, these things, the original ones were the size of a light bulb. So you can imagine how big and how hot the devices got. So even though they were great for amplification, they had huge drawbacks. But that's where silicon and semiconductors started to play a role, because instead of having something this big, you could go to something this big. And this is so small, I'm sure that you're going to find it very difficult to see on the screen. So this is a little transistor. And on my slides, you can see how this compares to a valve. So in my valve, I have a little signal that can come in and I can amplify it. And my transistor is made up in the same way. So the majority of them are made out of silicon. And what you have is also you apply a potential difference across the top. And in the middle, you can either switch it on and off and use it as a switch, or you can apply a small signal and you can have it amplified. So essentially, what we were doing with something that it was the size of a light bulb that we call a valve, we are now able to do with something called a transistor. And these were invented in the late 1940s. And that revolutionized our technology. But we got even better at manufacturing these things out of those silicon wafers that I showed you the photo of earlier. And so you don't just need a little transistor like this, but actually you could go to something like this. So this is a microchip. And if I show you the microchip, it actually has over 7 billion of these transistors, right? 7 billion of these, the equivalent of, on one microchip. So that's why our processing power and our computational power has become so much smaller than we used to have. In fact, if you look at that scale, that's the equivalent of having 500 of those little transistors on the surface of one blood cell. So that's the size of technology that we're talking about currently. And that means that if we look at devices that amplify, so sound devices, this is an old radio, right? And you can see here in this old radio, you have these valves and tubes that do the amplification. And then the new technology came along and we could make this amplification out of these transistors, and you can see them here. So we got transistor radios and they were way smaller. And now we have MP3 players that are even tinier. But like I said, it's not just about amplification, it's about computation, right? So these are photos of the earliest computers, and the earliest computers used these valves. And inside these computers, so this one, for instance, was one of the code-breaking computers used in the Second World War, and they needed around 5,000 of those tubes, of those valves, in order to work. 5,000. But some of the early computers, they needed up to 20,000. So they would be the size of enormous rooms. You need 20,000 of these, right? I mean, that's a huge amount of space that you needed. And even when you started replacing these valves with those little transistors, you still had huge devices. The reason why we need so many is because for every information point, so every bit of data, we need a 0 or 1. Now, these zeros or ones, we call each individual digit a bit, a binary digit, yeah? And 8 of those zeros and ones together, we call a byte. So if you've ever wondered what we're talking about when we talk about gigabytes and megabytes, we're talking about these zeros and ones. We group them in groups of 8. And, you know, before, we needed one of these would be 1 bit. 8 of these would give us 1 byte. So you would need 8 million of these to make something that was 1 megabyte, right? So this is why we're talking about such huge devices. And even after we started replacing those valves with these little transistors, look how big these devices were. This is a photo of is a hard drive, right, from 1956. And you can see here is they're having to use a forklift truck, right, to get it in a plane, right? And this is 5 megabytes, 5 megabytes. 5 megabytes is the equivalent of like one MP3, right? So that's all you can get on that. And it's huge because this is how much technology, this is how much physical technology you needed to cram into there. In 2001, when the first iPod was released, the selling point was you can get 1,000 songs in your pocket, right? And so this was already a 5 gigabyte device. So and this is something that now fits in our pockets. And the reason why is instead of having these valves and these transistors is that everything is built using these little chips, these little black chips, which take up hardly any room. So we've really been able to downscale our devices. And in fact, now, if you think about what you have in your own mobile phone, I've got a 64 gigabyte SD card. So you're talking about huge amounts of memory on something so small, right? These things are tiny. They're tiny. You lose them, right? If you take them out of your phone, you'll never find them again. So, so our technology's got smaller. This is really important because not only has it meant that our processing power is quicker and technology has become so small. I mean, back in the 40s, they said nobody will ever need a personal computer at home. And of course not when it takes up the size of a room, right? But now we've got technology that it fits in our pocket and we take it for granted. We wear it on our wrist and we don't think about it. So it's not only important to be able to scale these things down to make them faster and to make them more powerful, but of course, you're using less material and you're being able to mass produce them so they become cheaper. So we're all happy with that as well, right? But the other thing is, what else can we achieve with this technology? So, you know, supercomputers and that sort of thing. But this is a photo from a news article from a couple of years ago. And this was, at the time, the world's smallest computer that was ever made. You can see that here. But actually, what's next to it? This ugly white thing, that is a grain of rice, just to put that into perspective, right? So that is the smallest computer next to a grain of rice. And you go, okay, right, okay, that's interesting, right? But who needs a mobile phone that's that small because I'm never going to be able to find it? Well, that's not the point, right? The point is, where is technology going to go to next? And if we can start creating and fabricating things on this scale, then actually the uses are going to really change, and the uses are going to be endless. So these are some very cool examples of building electronics into a pill. So the idea would be you could swallow this pill and it would monitor all your functions, right? You don't keep having to go to the hospital for a test because for the number of hours that's in your system, it can monitor that information and it can send you the information to your telephone, right? You don't need to go into the hospital and to be wired up to these things. And I don't know, a lot of people these days are wearing activity trackers, right? And I don't know, I'm old school, right? So I wear an old school watch and I don't want to wear an activity tracker and a watch, I look like I'm wearing two watches. But here on the picture, you also see electronic tattoos. So the idea is you can make very, very, very small and thin circuits, and you can then stick these onto your skin. And by doing that, it will be able to monitor all of that information and be able to send it directly to a device. So these things are becoming smaller and smaller and more useful. So yeah, really technology, we don't know where it's going, and it's really exciting. And I kind of wanted to end by saying, you know, we curse our technology often, right? We often say, okay, like, oh, my phone, the app is not responding and my screen isn't working. Oh, my laptop's crashed again, you know? We're very quick to complain about these things. But the next time you're cursing your phone for not turning on or not working fast enough, just take a moment to reflect how far technology has come and what we've managed to achieve by using something as simple, as common and everyday as sand. And with that, I think I would pass over to David and we can open for questions. Thank you very much for your attention.
Thank you for your lecture, Donna. Let's see if we got some questions of our online viewers. We do have. Is there another material that can perform better than silicon?
Actually, there are a lot of different materials that are being used. So actually, I talked about diamonds, and I talked about how diamonds are semiconducting, but they're actually trying to experiment more with diamonds in electronics. So they are now being produced for computational reasons. So there's a lot of research being done in that area. But even though the majority of our devices, so these transistors and these chips, are made out of silicon, we actually use a lot of like gallium arsenide materials for creating LEDs. So even though they're semiconductors, they're not based on silicon. And we call those, because silicon's group 4 of the periodic table, if we use a mix of elements from group 3 and group 5 together, they bond in the same way as using a material from group 4, because it works out the same. You have a group 3 electrons and the 5 electrons, so you have the same kind of covalent bonding. And the research in that field, they're called 3-5 materials, and a lot of new semiconductor devices are being made of those 3-5 materials. And it's all a bit of an experiment, kind of mixing these different atoms to try and get the properties that you're looking for and the kind of things that you want, whether you want high temperature applications, high speed applications, those sort of things. So yeah, it's much, these days it's much broader than silicon, but it all started with silicon.
Okay, another question we got, as technology is getting smaller and smaller, what is your vision on how small it can get? Will humanity hit a limit? Do you believe that at one point we can have SD cards with petabytes of data? How small can we get?
Absolutely. Now, this is a huge challenge. So what I didn't mention is a law that we call Moore's law.
Moore?
Yeah. So Gordon Moore, he observed that, you know, the size of your device is getting smaller, is getting half of the size every 18 months, 2 years on average, right? What that means is that actually you're able to integrate double the number of components onto one chip, onto the same piece of silicon real estate. We talk about silicon real estate, right? So you're basically able to cram more and more onto one chip every 18 months. And that is, you know, you see that when you look back at old technology and you laugh at how large, like, you know, you watch a movie from the 80s and it's all huge, these huge telephones. So yeah, things are getting smaller, but way back even in the 90s, people were saying, it's going to be the end of Moore's law. It can't continue. And actually, you know, every year I read another paper that says it can't continue, and then they're finding more and more ways of doing that. I mean, IBM were experimenting with devices that they can literally move atom by atom around. Mm-hmm. You do get problems as you make things smaller. Electrons, they can tunnel through the different regions. So, you know, I showed the 3 different layers that you have in a transistor. Of course, if you make that smaller and smaller, the electrons can shoot through the layers and basically destroy the device. So it is a huge challenge. But they're now trying like to build like 3D structures as well, because we've generally built our structures in a 2D way. So you see how those layers are built up, and it's about building the layers in a slightly different configuration. So there's a lot of research being done there. But yeah, whether we need to move to something else in the future, I don't know.
And another question about currently quantum computing is on the rise. It is said that it is a significant increase in computing power for certain applications and that the current consumer does not benefit that much. You also stated that in the 40s, nobody thought they needed a personal computer. Do you think, the question is, in 50 years or so, the average consumer has an application for quantum computing?
Yeah, I mean, it's very difficult to predict the future, right?
That's true. That's true.
So I wouldn't dare comment on what I think will happen in the future. But I guess it's like all of these things that there are limits. It's like with the current vaccine, right? There's current limits because of the cold temperatures that these things need to be kept at. Because I mean, if there were many ideas with superconducting materials, for instance, that we were going to have maglev trains all over the world and this kind of thing. But it's the expense and it's the logistics that holds you back with those kind of technologies. So you're always waiting for that next breakthrough. And that's not to say that it can't happen, but I think it's very difficult to predict what is going to happen. Absolutely.
I've got a few more questions before the end. Does conductivity end somewhere around a certain high temperature, or does it still increase at extreme high temperatures?
Well, eventually you would get the breakdown of the material, because the way that these semiconductors conduct, they conduct in that way because they're regularly structured into these lattices. So the pure silicon is in a regular crystal of silicon. And that means that you have specific energy levels that these transitions take part in. And the minute you heat a material to the extent that you lose that atomic regularity in the structure, then you also lose those semiconducting properties. And you can look at it. I said that semiconductors, they're halfway between a conductor and an insulator. But insulators, actually, they have the same property. It's just you can't get them to the temperatures that are high enough without destroying them. So that's where your limit becomes. So it's the physical properties that stop you going any higher. And don't forget that it's only those electrons that are in the outer shell that are liberated and take part in that conduction. So once those have been liberated, you can't go any further either. You're not going to liberate anything from the lower shells. They're too stable in their structure.
Okay. And then we have the last questions concerning diamonds. Is the carbon used to manufacture synthetic diamonds extracted from the atmosphere? That's one question. And another question is real diamonds or synthetic ones? I can't imagine, and I thought that also, that using real diamonds would be cost effective.
Yeah, no, for electronic properties, for electronic applications, it's man-made diamonds that they're using. When I was a student, I did a 3-month internship in a diamond physics lab, and we created them using chemical vapor deposition. So basically, you start with a very small seed of carbon, and in a very high temperature, high pressure system, you can flow a sort of air right over which contains carbon ions, and they will deposit on that seed and they will grow. So it's kind of a mix. You do need the high temperature and pressure, like how a real diamond is created. But I think there are different techniques for doing that as well. And in fact, it's become so common. There's I don't know if the company still exists, but there are certain companies that it's kind of gory. You can send the ashes of your loved one or your pet, and you can send it to this company, and they will make a man-made diamond for you out of the carbon remnants of your loved one. So if you want to wear a ring with your old grandmother, you can carry her with you for the rest of your life.
Yeah, and then you put a chip on it, and then you implant it near your heart, so that's real. Then the circle is round. Well, this is the end. Once again,
applications are endless.
Yeah, endless. Once again, thanks a lot, Donna, for enlightening us. Thanks for watching at home. For the viewers at home, the use registration link can appear any second now in the chat boxes of our socials. Hope you enjoyed it and hope to see you at our coming events. For example, next week, same time, about the upcoming elections. Do vote and see ya.
We be